Hi everyone, my name is Neha Kardam and in this lecture we are going to learn about counters. This is the third part of counters and in this lecture we will be covering frequency division using counters, using counter ICs, magnitude comparators, troubleshooting hints, application DIY, experimental tachometer. And before that, all these topics we have covered in the last two lectures. Now let's first start with counter used for frequency division. So you see that this is our counter, up counter, and it is for 4-bit 4-bit up counter, and we have 800 hertz frequency is going into this up counter, and this up counter is going to divide the frequency. So this is a really interesting and common use of counter for frequency division, and we are going to see how it's going to divide the frequency. So if you look here, after going this 100 hertz clock into this first flip-flop, then what will happen? The clock will become 400 hertz because the frequency will be divided by 2 when it goes through this first flip-flop. Okay, and at the second flip-flop, when it goes through the second flip-flop, then it will be divided by 4, which will make it 200 hertz. And then further, if it is if it goes through the third flip-flop, then the frequency will be divided by 8. And then if it goes through the fourth flip-flop, then the frequency will be divided by 16. So this is the way how we do it. You can also, the other way to understand is that 800 hertz frequency clock, when going into the first flip-flop, then it provides f by 2. F is the frequency, f by 2 frequency it will produce at the output. And then again, like in each flip-flop provides basically f by 2 frequency change. So when this frequency goes in here, this whatever the frequency which is left here, 400, so 400 divided by 2, and then 200 divided by 2, which makes it 100. That's what you see here. And then 100 divided by 2, that makes it 50. So that's another way of understanding it. And then you can also verify this from the waveform of the timing waveform. You see that this is our clock and this is our QA. So this QA is this representing your ones output, okay, when the frequency is 400 hertz. So you can see that this clock is of 100 hertz frequency, and how it has reduced to half, which is your 400 hertz, and you can see that through the waveform also. And then further, this clock has been when this is taken as a clock into the next flip-flop, then what will happen? There is another division of the frequency takes place of f by 2, and that you can see over here that frequency division took place, and here the frequency is widespread, and it is 200 hertz, half of what we had before. And then again, when this frequency goes into this flip-flop as a clock, then this is going to provide f by 2 frequency division, and that's what you see here. So in this one we have 400 hertz. So in the next one we are going to have 200 hertz. And then further from 200 to 200 hertz, and this is 100 hertz actually. This is 400, 200, and this is 100 hertz, and from 100 hertz to this is going to be 50 hertz. And that you can see also that how far away it is. The frequency has reduced to 50 hertz from 800 hertz to 50 hertz. And then you can add more modification depending upon how much frequency division you want. So for example, if you just need to have 200 hertz frequency, then you do not need to add these two flip-flop. You can just use 2 flip-flops. And in case you just want to have 400 hertz frequency, then you can just use a single flip-flop. So based on the application and use, you can construct your circuit using the flip-flops. and it will create the frequency divisor based on how many flip-flops you have used and what frequency you are sending into the clock of the first flip-flop. Now let's go to the next slide, which is the quiz. And the first question says, what is the output frequency from the first JK flip-flop with an input frequency of 3200 Hertz? So it is asking like what you're going to have at this point, what frequency you are going to get. So we know that we have like 4 flip-flops, and each of them each will basically divide the frequency by 2. So when it goes through the first flip-flop, then it will divide the frequency by 2, and the half of 3200 is 1600, and that's going to be our answer. Now, what is the output frequency of the 2's JK flip-flop with an input frequency of 3200 Hertz? So we want to know the output of 2's JK flip-flop, and what will be the frequency over here. So we already know the f by 2 already we took was 1600, and then if you again divide that frequency, so 1600 divided by 2 is what is 800, so that's what you are going to get here. So 800 is your answer. And then what is the output frequency from the 4th JK flip-flop with an input frequency of 3200 Hertz? So it is asking what will be the output frequency at this force output point. So again, you're going to divide this 800 by 2, which is going to be 400. So 400 Hertz is our answer. And then what is the output frequency at 8s? So at 8s, you are going to divide whatever your frequency was previously by 2. So it is going to be 200. So you saw that how the frequency, the clock input has changed from 3200 to 200 Hertz using these 4 flip-flops. Now there is another question. The 8's output from the 4-bit counter is referred to as the divider by 4 or divider by 6. So if you calculate, what did we do? We divided each flip-flop divide by f by 2 based on what clock it is receiving. And at this point we received 200, we had 200, and so we can calculate that frequency is going to so this is dividing by 16. If you divide it by 16, then you will get 200. So that's one way of remembering that each of the flip-flop is going to divide by 2, f by 2. Otherwise you can remember this way, that you are going to get the frequency f by 2, where f is 3200, and this one will be f by 4, where f is going to be 3200, and this is going to be f by 8, f is again the 3200, and then this is going to be f by 16, where f is again going to be your input clock frequency. So the answer for this is going to be divide by 16. Now next topic is using the 7493 counter IC. So counters, they are available in IC forms, and you have been using them in the lab experiments also. They are either ripple counters. Ripple counters are called your asynchronous counter, and one of the example for that is given here, 7493 IC, which is a asynchronous counter, or synchronous counter, and this another example is given, 74192 IC counters. They are available. And here you see this is the 7493 IC, which is the asynchronous counter, and it has 4 binary output, and then input clock is going in here, and then you have 5 volts power VCC going in here. Now let's see. So this says it is a 7493 counter IC wired as a 4-bit binary counter. Now let's see what will happen. You are giving input clock frequency as 1600 Hertz. Then what frequency you are going to get at this one's output? So at this point you are going to get f by 2, which is going to be 800, based on the clock frequency. So if you divide 1600 by 2, you will get 800. And then what is the frequency you're going to get at this point? So I told you either you can do like f by 2 and then just go on, or you can just do like for this case it is going to be f by 16. So if you divide this frequency by 16, then you're gonna get you're gonna get the 100 hertz. So that's what the answer is. And at this point, what is going to be the frequency? So this is f by 4, where f is 1600, or you can take the input clock from here, like you can use this and divide it by 2, and that will give you 400. So 400 hertz is the answer. Now, the next topic is the magnitude comparator. So magnitude comparator, it is a combinational logic device that compares the value of two binary numbers and give the output based on those two input binary numbers by doing the comparison. So there are three comparison outputs we have, whether A is equals to B, where A and B, they both are two inputs, and it do the comparison. So three comparison can be made for if you have like two inputs. Either they can be equal, or A can be greater than B, or B can be smaller than A can be smaller than B. So these are the three output combination you can have, and these are the four inputs A and 4 inputs B, and these are the outputs which are generated based on what the input you receive, and the comparison is made, and then based on that the output will be turned on. Okay, so let's take an example. So if you have an input binary going in, so this is 0001, so which means 0001, and then you have 1100 going in for B. So if you compare these two, which one do you think is greater? So in this case, B is greater than A, because this A is your 1, whereas B represents your 12. So which means that A is smaller than B, so this is going to be high, and that's why you have high here. Let's say if you have input binary 1111, and then if you have input binary for B is 0110, so definitely this is smaller than this binary number, so A is greater than B in this case. So in this situation, your this A is greater than B is gonna turn high. And if you have like same input, you see that they both are 7 in decimal, so in that situation they both are equal, so in this case this is going to turn high. So this magnitude comparator you can use in different applications. For example, they can be used in central processing units, microcontrollers. They are also used in control application, in which the binary numbers, they represent physical values such as position, temperature, etc. And they are compared with some reference value. And these magnitude comparators, they are also used in process controllers, and for servo motor control. They can be used in power verifications, in biometric applications. There are many uses of magnitude comparator, and maybe you can use in your project also to compare two bits. Now let's see next. Next we have a quiz. So the first question says 74HC85 comparator IC compares two 4-bit dash is either binary or decimal numbers A and B, and generates one of the three outputs including these. So definitely it's going to be the binary number, not the decimal, because we sent here the binary number. So the answer is binary. Now second is which output of the comparator IC will be activated with these two 4-bit binary numbers as inputs. So we have 0101 and we have 0101. They both are equal. So in that case, A is going to be equals to B. So this is going to be turned on. Now when you have 0101 and this is 1011, so in this case A is smaller than B. This is a greater binary number, this is a smaller binary number, so this is going to be A is less than B, which is this one. And then in this one, A is clearly higher than B. So this is going to be A is greater than B. So if you see this number, this is your 13 in decimal and this is 10 in decimal. So 13 is greater than 10, and that's how also you can check it out. So A is greater than B, so that's what our answer is. Now next is simple troubleshooting hints. So these are the couple hints which I'll be showing you, and you can use this when you do the lab experiments. So first thing you can do is when you touch the IC, you see whether the IC is hot or not. If it is hot, then maybe the IC is damaged and due to which the circuit is not working properly. And second, look for broken connection, signs of excessive heats. See if your connections are wired up correctly, because any wrong connection can make short circuit, and which can leads to excessive heat. Look for smell. If you have like heating in your circuit, then it might produce some bad smell, and then that's another way of looking at the troubleshooting the circuit. And then check for power source. See how your power source is connected, whether it is turned on or it is not. Your power, your circuit is correctly grounded or not, and you're giving power to the right component or not. So all these things you have to check into your circuit. And then next is the trace path of logic through circuit. So see like how your current is flowing and see if it is matching with the design or not. And if it is matching, then everything works fine. If it is not, then there is some problem with the circuit. Know the normal operation of the circuit. So when you design a circuit, you should be aware of what you are doing. At least you should know theoretically that how the circuit should work. And that's a basic rule, and if you know that, then you can basically predict that what may have went wrong and due to which the circuit is not working. So these are the some simple troubleshooting steps you can take when you are working in a lab, and check for any faults using these simple hints. Now next is quiz. The first 3 steps in the troubleshooting are the use of your senses, which is to feel the top of ICs for overheating, to dash for broken connections, and to smell for sign of overheating. So first 3 steps which we saw was to feel it, and to smell it, and to look it, to see. Okay, these are the 3 senses, first 3 senses which we use. So the answer is going to be here, look. So I'm going to read this sentence again. The first 3 steps in troubleshooting are the use of your senses, to feel the top of the ICs for overheating, to look for broken connections, and to smell for signs of overheating. Second is the fourth step in troubleshooting is to use a simple handheld instrument called a dash to check the power source at each IC. So I haven't discussed this in this previous slide, but if you think about it, then what that would be? It's going to be the logic probes. You use the logic probe to check the power source at each IC. Your knowledge of the normal operation of the circuit and equipment is very important in troubleshooting. Is it true or false? It's straightforward question. So we know that we do need to know the normal operation of the circuit when we perform it in the lab. So this statement is true. Now application DIY experimental tachometer, and this is, you see here is the block diagram, and you can design this this experiment in your lab also. All of these things must be available in the lab. You can use 4-bit BCD counter, and then decoder you can use, and then you can use a display. And then here you give the clock, one shot clock you give, and you can use a Hall effect sensor which will connect to this counter, and then use some rotating motor, and as the rotor rotates, this Hall effect basically sense the rotation, and it will convert the rotation into the number of pulses, and those pulses will go into the counter, and counter will basically count those number of pulses, and decoder will basically decode the number of pulses counted into the four digit display. So you see here experimental tachometer. The tachometer measures the angular velocity, and this is the basic function of the tachometer, and of the rotating disc with an output in RPM, which is revolution per minute. The 4-digit BCD counter IC counts the input pulse from the Hall effect sensor generated in 1 minute. The counter output 4 digits is coded and displayed on the 4-digit 7-segment display. So, and then this is your, I'll go back to this one. This is your inputs. Hall effect sensor is triggered by the magnet embedded in the rotating disc, which is 1 pulse per revolution, and it generates the pulses as I told you, and entering the clock input into the counter. A one-shot multi-vibrator generates. So this circuit you will have to make a one-shot multi-vibrator, and it will generate a 1 minute negative pulse which lash the count inside the counter at the end of the 1 minute. And then you have a BCD counter and display multiplexer. So this four BCD cascade counters with latched output are housed in the counter IC, and the counter IC will also contain a section of the digital multiplexing, which will allow each 7-segment display to light on and off each in turn in rapid session. So that's what the function of the counter is. And then we have BCD to 7-segment decoder and driver, and the decoder IC, it basically translates BCD to 7-segment code. The segments of all 4 common anode LED display, they are basically activated at the same time, but only one display lights briefly at a given time, because the anode of the LED displays are multiplexed by the BCD counter multiplexer ICs. And then you have 4-digit 7-segment display. So 4 common anode 7-segment display you can use, which will be used in this tachometer, and they can indicate speed ranging from 0001 through 9999 RPM. So this type of circuit you can make in the lab using the lab equipments, and you can operate an experimental tachometer. So let's see what it says here. DIY experiment tachometer, use lab equipments to set up and operate experimental tachometer. Your lab manual may have tachometer circuit using some common sensors, counters, displays, multiplexers, decoder, 7-segment displays. So you can perform this experiment and let your instructor know that how it works out. So this was the end of the lecture, and these are the review of the topics which we have covered in the counters. So in this 3 lectures of counters which um, we covered all these topics. We learned about the basic counters, up counters, down counters, asynchronous, synchronous, decade counters, self-stopping counters. We learned about how we can use counter in an application of frequency as a frequency divider. We learned how to use the IC, counter IC. We learned about magnitude comparators, which compare the magnitude of the two inputs, binary inputs. And then we learned about simple troubleshooting hints, in which we learned about like the basic troubleshooting hints are to use your senses, which means you will look for fault. You will feel if the IC is hot, and you can see if you can basically smell if there is any overheating. So stuff like that we discussed in there. And then we talked about applications, and this is the DIY experimental tachometer which you can basically build in the lab. So this is the end of the lecture. Thank you so much for watching.